sump pump control panel has two capacitors wired in series inside it. When power is applied, the pump contactor closes for 5 or 6 seconds prior to tripping the circuit breaker. The capacitors seem to be alright and the pump motor mega tests great at 50 megohms. Here are some ideas of what might be happening. Let's explore potential causes for this issue. A locked rotor may be present. The motor could be drawing excessive current due to a jammed impeller or a bearing failure. A malfunctioning contactor could also be the culprit. The contactor might not be closing properly or failing to hold closed. A wiring issue such as loose or damaged wiring connections can cause resistance and voltage drop. There may be a fault in the control panel circuitry that is causing the circuit breaker to trip. The pump might be experiencing an overload condition, drawing more current than the circuit breaker is rated for. Here are some troubleshooting steps you can follow. Firstly, disconnect the motor. Isolate the motor from the control panel to eliminate any motor-related issues. Secondly, check the contactor. Use a multimeter to test the contactor's resistance and ensure it is closing and holding closed properly. Thirdly, inspect the wiring. Check for any loose or damaged connections in the control panel and motor wiring. Fourthly, test the control panel circuitry. Use a multimeter or oscilloscope to verify that the control panel is functioning correctly. Fifthly, check for overload. Measure the current drawn by the motor to ensure that it is within the circuit breaker's rating. Let's consider some additional factors. The capacitors may be discharging into the circuit breaker when power is applied, causing a momentary surge of current. The pump may require a higher starting torque than the capacitor combination is providing. The pump may not be primed properly before power is applied, causing it to draw excessive current. Here are some recommendations. Replace the motor if mega testing indicates a problem. Replace the contactor if found to be faulty. Ensure all wiring connections are secure and undamaged. Contact the control panel manufacturer for technical support if necessary. Focusing on the locked rotor, we will discuss this more. A locked rotor condition occurs when the rotor of an electric motor is prevented from turning. This can happen due to mechanical obstructions, bearing failure, or a jammed impeller. When the rotor is locked, the motor draws a very high current, often several times its normal operating current. This excessive current can quickly overheat the motor windings and trip the circuit breaker. To diagnose a locked rotor, first, visually inspect the pump and impeller for any obstructions. Try to manually turn the impeller. If it is difficult or impossible to turn, there is likely a mechanical issue. If the impeller turns freely, the problem might be internal to the motor, such as a bearing failure. To further investigate, disconnect the motor from the power supply and use an ohmmeter to measure the resistance between the motor terminals. A very low resistance reading indicates a short circuit in the motor windings, which can also cause a locked rotor condition. If you suspect a locked rotor, do not attempt to run the motor for more than a few seconds, as this can cause permanent damage. Repairing a locked rotor often involves disassembling the pump and motor, clearing any obstructions, replacing damaged bearings, or rewinding the motor. Now let's talk about the contactor. The contactor is an electrical switch that controls the power supply to the motor. It is designed to handle the high current required to start and run the motor. A malfunctioning contactor can cause several problems, including the motor not starting, the motor running intermittently, or the circuit breaker tripping. Common issues with contactors include worn or corroded contacts, loose connections, and a faulty coil. To check the contactor, first disconnect the power supply to the control panel. Then visually inspect the contactor for any signs of damage, such as burnt or cracked components. Use a multimeter to test the continuity of the contacts. When the contactor is closed, there should be a low resistance between the terminals. When the contactor is open, there should be infinite resistance. If the contacts are worn or corroded, they may not make good contact, causing a voltage drop and excessive current draw. Also, check the coil of the contactor. Use a multimeter to measure the resistance of the coil. If the resistance is too high or too low, the coil is likely faulty and needs to be replaced. Loose wiring can lead to increased resistance, voltage drops, and potential arcing, all of which can cause the circuit breaker to trip. Inspect all wiring connections in the control panel and motor junction box. Look for loose screws, corroded terminals, and damaged wires. Tighten any loose connections and replace any damaged wiring. Pay close attention to the connections at the circuit breaker, contactor, motor starter, and motor terminals. Ensure that all wires are properly sized for the current they will carry, as specified in the National Electrical Code, NEC, Table 310.16. If you find any evidence of arcing, such as blackened or melted insulation, clean the connections thoroughly and consider using a wire brush to remove any corrosion. Also, make sure that the wires are properly insulated and protected from physical damage. Testing the control panel circuitry involves checking the various components and connections within the control panel to ensure they are functioning correctly. This includes checking the voltage levels, current flow, and signal integrity. Use a multimeter to measure the voltage at different points in the circuit. Verify that the voltage is within the specified range for each component. Check the power supply voltage to ensure it is stable and within tolerance. Look for any voltage drops or fluctuations that could indicate a problem. If you have access to an oscilloscope, you can use it to analyze the waveforms of the signals in the control panel. This can help you identify any distortion, noise, or other anomalies that could be causing the circuit breaker to trip. Check the timing and synchronization of the signals to ensure they are within the specified parameters. If you find any faulty components, replace them with new ones that meet the original specifications. Make sure to properly ground all components and connections to prevent electrical noise and interference. Checking for overload involves measuring the current drawn by the motor and comparing it to the circuit breaker's rating. Use a clamp meter to measure the current flowing through the motor wires. Measure the current under normal operating conditions and during startup. Compare the measured current to the circuit breaker's amp rating. The motor's current should not exceed 80% of the circuit breaker's rating to account for inrush current and other factors. If the motor is drawing more current than the circuit breaker is rated for, it could be due to a locked rotor, a malfunctioning contactor, or an overload condition. A capacitor discharge can occur when the capacitors in a control panel release their stored energy into the circuit breaker when power is applied. This can create a momentary surge of current that trips the breaker. To mitigate this issue, consider using a slow-blow circuit breaker, which is designed to handle brief surges of current without tripping. You can also add a resistor in series with the capacitors to limit the discharge current. Make sure that the resistor is properly sized to handle the voltage and current. The pump may require a higher starting torque than the capacitor combination is providing. The starting torque is the amount of rotational force that the motor can produce when it is first turned on. If the starting torque is insufficient, the motor may struggle to overcome the inertia of the pump and impeller, causing it to draw excessive current and trip the circuit breaker. To address this issue, consider using a different capacitor combination that provides a higher starting torque. Consult the motor manufacturer's specifications to determine the appropriate capacitor values. You can also try using a soft starter, which gradually increases the voltage applied to the motor during startup, reducing the inrush current and increasing the starting torque. Another option is to use a variable frequency drive, volts per hertz, which allows you to adjust the motor's speed and torque to match the pump's requirements. If the pump is not properly primed before power is applied, it may draw excessive current. Priming the pump involves filling the pump casing and suction line with water before starting the motor. This ensures that the pump can immediately begin pumping water, reducing the load on the motor. If the pump is not primed, the motor may have to work harder to overcome the air resistance in the pump casing, causing it to draw more current. To prime the pump, first close the discharge valve. Then open the priming valve and fill the pump casing and suction line with water. Once the pump is full, close the priming valve and open the discharge valve gradually. Start the motor and observe the current draw. If the current draw is still excessive, stop the motor and repeat the priming process. You may need to add a check valve to the suction line to prevent the water from draining out when the pump is not running. Megger testing can reveal insulation breakdown or winding shorts within the motor. The megger applies a high voltage direct current, typically 500 volts or 1000 volts, to the motor windings and measures the resistance to ground. A high resistance reading indicates good insulation, while a low resistance reading indicates insulation breakdown or winding shorts. A reading of 50 megohms is generally considered to be acceptable, but the specific threshold may vary depending on the motor's voltage rating and application. If the megger test reveals a problem, the motor should be replaced or rewound. The NEC addresses motor insulation requirements in Article 430. Replacing the contactor is necessary if it is found to be faulty. A faulty contactor can cause various issues, including the motor not starting, the motor running intermittently, or the circuit breaker tripping. To replace the contactor, first disconnect the power supply to the control panel. Then remove the old contactor and install the new one in its place. Make sure to properly connect all the wires to the new contactor. Use a wiring diagram to ensure that the connections are correct. Once the new contactor is installed, test it to make sure it is functioning properly. Use a multimeter to check the continuity of the contacts and the resistance of the coil. Ensuring all wiring connections are secure and undamaged is crucial for safe and reliable operation. Loose or damaged wiring connections can cause resistance, voltage drops, and potential arcing, all of which can cause the circuit breaker to trip. Inspect all wiring connections in the control panel and motor junction box. Look for loose screws, corroded terminals, and damaged wires. Tighten any loose connections and replace any damaged wiring. Pay close attention to the connections of the circuit breaker, contactor, motor starter, and motor terminals. Ensure that all wires are properly sized for the current they will carry, as specified in the NEC. If you find any evidence of arcing, such as blackened or melted insulation, clean the connections thoroughly and consider using a wire brush to remove any corrosion. Also, make sure that the wires are properly insulated and protected from physical damage. If you are unable to resolve the issue on your own, it is best to contact the control panel manufacturer for technical support. The manufacturer's technical support team has specialized knowledge of the control panel and can provide guidance on troubleshooting and repair. They can also provide information on the proper operation and maintenance of the control panel. When contacting technical support, be prepared to provide the model number and serial number of the control panel, as well as a detailed description of the problem. This will help the technical support team to quickly diagnose the issue and provide a solution. Finally, remember that working with electrical equipment can be dangerous. Always take precautions to protect yourself from electrical shock. Disconnect the power supply before working on any electrical components. Wear appropriate personal protective equipment, such as safety glasses and insulated gloves. If you are not comfortable working with electrical equipment, hire a qualified electrician to perform the work. Following these troubleshooting steps and recommendations can help you identify and resolve the issue of a sump pump tripping a circuit breaker.